Welcome back to our deep dive, looking at what's buzzing in the biochar world this week. You, our listeners at Biochar Today, flagged some really fascinating stuff.
Yeah, it's quite a mix.
We've got new research on activating biochar with syngas from France, then a really critical story about saving salmon out in Washington state,
That one's powerful.
and finally some, let's say, surprising work from Argentina, looking at biochar as a sustainable electrode. Quite the range.
It really is. Shows how versatile this material is becoming, doesn't it? From basic science to, real-world environmental fixes and even high-tech applications, clearly hitting a chord with the Biochar Today community.
Definitely. So let's jump into that first one, the work out of Nantes Université in France. They're using syngas to activate biochar.
That's right. Syngas, mostly hydrogen and carbon monoxide. They've got this patented pyrolysis reactor, and the really clever bit is what they call in situ partial reduction.
Okay, in situs. So happening right there.
Exactly. They've added this zone down at the bottom of the reactor. Freshly made, really hot biochar meets hot syngas coming from another part of the same system.
So it's like an immediate upgrade step,
Right.
build right in.
Mm.
And the goal is boosting the surface area.
Precisely. The specific surface area, that's, the total interactive surface on the char, super important for lots of its uses.
Right, like in farming,
Mm-hmm.
for holding on to water, nutrients, that kind of thing.
Exactly. A bigger surface area, it's like a better sponge, holds more water, grabs more nutrients, makes them available for plants. And it's also key for locking up contaminants.
Makes sense. So how much of a boost are we talking?
Well, the numbers are pretty impressive. They measured an increase on average of 250 square meters per gram.
Whoa.
Yeah. And the pine bark biochar they started with, it already had about 200 square meters per gram, which is decent.
So this process can, like, more than double it.
In some cases, yeah.
Yeah.
A really significant jump. That's probably why it caught people's attention over at Biochar Today. Performance matters.
And they managed this without hurting the carbon content. That stayed high.
It did. Still around 90% carbon, which is great. You need that high carbon for stability in the soil, long-term carbon storage, all things that Biochar Today readers care about.
Okay, but I saw there's a bit of a trade-off. The process uses up some of the carbon, about 20%.
Yeah, about 20% of the biochar's carbon gets consumed in this reduction step. But here's the interesting part. It's not just lost.
Oh, where does it go?
It actually enriches the syngas, makes Yeah. the syngas itself more valuable.
Ah, okay. So you could potentially use that enriched syngas for something else.
Exactly, like producing biomethane or maybe biohydrogen, even biokerosene. It sort of fits into this circular economy idea. The byproduct of one process becomes feedstock for another. That whole system thinking probably resonates.
And environmentally, this physical activation,
Mm.
using the system's own gases, that's better than chemical methods.
Oh, definitely. Chemical activation often uses some pretty harsh chemicals, acids, bases,
Yeah.
stuff that needs careful handling and disposal and might even leave residues.
Right.
This method avoids all that. It's cleaner, potentially cheaper in the long run, and just uses what's already there. Big plus for sustainability, which is always a focus for Biochar Today.
Did they test it under different conditions? Like different amounts of wood going in?
They did. They varied the flow rate of the pine bark biomass, and they found the increase in surface area was pretty consistent.
That sounds promising for,
Yeah.
Actually using this technology.
It suggests it could be quite robust, yeah, and adaptable. The temperatures in that zone get pretty high, over 500 Celsius.
Okay.
And the recirculating syngas bumps the biochar bed temp up by another 200 degrees C on average. So it takes energy, but the system itself provides a lot of that heat. Efficient design.
But back to that trade-off, the yield. It drops from around 38% down to 28%. That's quite a bit less biochar overall.
It is, and that's the key decision point, isn't it? If you need really high-performance biochar for a specific, maybe high-value application like targeted pollution cleanup, or maybe those electrodes we'll talk about later, then maybe getting less biochar, but much better biochar, is worth it. You might use less to get the same effect, but if you just need bulk material for, say, general soil amendment across large areas.
Then maybe the higher yield's more important for cost.
Exactly. It lets you tailor the biochar, quality versus quantity, depending on the job. That kind of nuance is important for the informed folks following Biochar Today.
Makes perfect sense. Okay, let's shift gears. This next story. Wow. King County, Washington. Saving salmon. That really caught my eye.
Yeah, this one's less about the material science itself and more about a really direct critical application. It's pretty sobering, coho salmon dying before they can even spawn.
A mystery for a while, right?
For a while, yeah. But scientists figured it out. It's a chemical called 6-ppd quinone, or 6-ppdq.
Yeah.
Comes from a preservative used in tires.
In all tires?
Pretty much all tires, yeah. The dust wears off onto the rows.
And then rain washes it straight into the streams. Oh, man.
Exactly. And it's incredibly toxic to coho salmon specifically.
So where does biochar come in? How can it possibly help with tire dust?
Well, researchers at King County's Water and Land Resources Division, they were already working on improving stormwater filtration systems. And they stumbled upon, well, maybe not stumbled, they developed a soil mix that works wonders.
A special mix. What's in it?
It's fairly simple, actually. Sand, some coconut core fiber, and biochar.
Ah, there it is.
Yep. The stormwater runoff basically filters slowly through this mixture. The sand gives it structure, the core helps with water flow, and the biochar, with that high surface area we were just talking about.
It traps the 6-ppdq.
It seems to. It
Yeah.
traps that chemical and likely other pollutants too. It acts like a natural Brita filter for the stream, basically.
And the results were good.
Good is an understatement. They did lab tests, put coho in unfiltered stormwater runoff. Nearly 100% died.
Oh, awful.
Then they put coho in the same stormwater after it had filtered through this biochar mix. 100% survival.
Wow. That's incredible. Night and day.
Absolutely. It's such a clear, direct demonstration of biochar's protective power, moving it way beyond just helping soil. This is about saving a species, cleaning up ecosystems. Powerful stuff for the Biochar Today readers to see.
No kidding. Are they actually using this yet, or is it still just lab work?
They're moving fast, planning a full-scale pilot project now to test it in the real world.
Right.
And King County is actively mapping out the 6-ppdq hotspots, figuring out where the problem is worse so they can prioritize putting these filters in the right places.
Smart.
They've even updated their official stormwater management guidelines already, allowing this mixture to be used in certain areas.
That's great. It shows real commitment to using the research.
Exactly. It's a fantastic example for anyone following biochar, showing it solving a really complex, urgent environmental issue with, tangible life-saving results. It really broadens the perspective on what biochar can do.
Absolutely. A very hopeful story, actually. Okay, final topic for this week's deep dive. Takes us down to Argentina. And this one sounds, well, a bit more technical. Biochar as an electrode, replacing graphite.
Yeah, this one probably appealed to the more engineering-minded folks in the Biochar Today network. We're talking about microbial electrochemical technologies, METs.
METs. Okay, what do they do?
Basically, they use microbes, bacteria to do useful things like clean wastewater or even generate a bit of electricity. They're fascinating systems.
And they usually use graphite for the electrodes.
Right. Graphite conducts electricity well, which the microbes need to, dump their electrons onto the electrode. But making graphite, it takes a lot of energy. It can have a significant environmental footprint.
Got it. So the idea is, can biochar do the same job, but more sustainably?
Precisely. This Argentinian study looked at biochar made from papyrus.
Yes, the papyrus.
Like ancient Egypt papyrus.
The very same plant residue, yeah.
Yes.
Burning residues. They pyrolyzed it at different temperatures from 500 up to 1,000 degrees Celsius.
Why the different temperatures? Because temperature drastically changes biochar's properties, especially its electrical conductivity. Higher temperatures generally mean better conductivity, closer to graphite, but also means more energy use.
Right, so they compared these different biochars to standard graphite, seeing how well they supported these electricity-making bacteria, Geobacter sulfur-reducens.
Exactly. They looked at how much current the bacteria could generate using each electrode material.
And what did they find? Did the biochar work?
It did. Interestingly, the biochar made at lower temperatures, like 600 degrees C. It generated about half the current compared to the high-temp biochar, the graphite.
Okay, so performance-wise, not quite as good at the lower temp.
Not quite as high, no. But here's the kicker, and this is likely what got the Biochar Today crowd excited: the environmental footprint.
Ah, the sustainability angle again.
Hugely important here. Producing that 600 degrees C biochar, way less energy, much lower carbon emissions compared to making graphite.
How much lower?
Significantly lower. In fact, they calculated that the 600 degrees C biochar could actually be carbon positive.
You mean carbon negative, like it stores more carbon than it emits.
Exactly. Sorry, carbon negative or a positive footprint in terms of sequestration, because the biomass locked up carbon and the production process was relatively low energy. That's a massive potential advantage over graphite.
A carbon negative electrode material. That does sound pretty revolutionary.
It really is. Now, the conductivity did get better at 1,000 degrees C, much closer to graphite.
But the energy cost goes up and the carbon benefit goes down.
Precisely. So the low temp biochar hits this sweet spot, decent enough performance, maybe not top tier yet, but potentially much, much better for the planet.
What about holding up physically?
Yeah,
Electrodes need to be kind of tough, right?
that's a fair point. They did find the biochar wasn't as mechanically strong as graphite. That's definitely an area for more work, maybe reinforcing it or using it in composites, something the Biochar Today community will likely keep an eye on.
So the takeaway is low-temp biochar looks like a really promising, sustainable, maybe cheaper alternative for these MET systems, even if the raw performance isn't quite graphite level yet.
That sums it up nicely. Lower production cost, potentially carbon negative. It opens up a really interesting pathway for greener electrochemical technologies, using biochar in ways we probably didn't imagine just a few years ago.
Wow. Okay, so wrapping up this week's deep dive, looking at what the Biochar Today community found interesting. It's quite a journey, isn't it?
It really is.
From fundamental work tweaking biochar properties with syngas
Yeah, the core science.
to using it as a lifeline for salmon facing toxic runoff,
That direct environmental impacts.
and then exploring its potential to replace conventional materials in really advanced tech like METs.
It covers such a broad spectrum. It just shows how this material made from biomass can be engineered and applied in so many different impactful ways.
Tackling agricultural needs, solving pollution problems, offering sustainable industrial alternatives. It's pretty amazing.
The innovation happening is really impressive, and you can see why these diverse stories resonated with the Biochar Today readers. There's just so much potential being unlocked.
Definitely feels like a space to watch. Well, we hope this run-through of what caught your collective eye this week has been useful. Lots to think about.
For sure.
Thanks for joining us on this deep dive,
Really?
and maybe something to ponder for next time. Given how biochar is turning up solutions in soil, water, and even electronics, what a seemingly unrelated field might be the next surprising place where biochar makes a difference worth thinking about.